Hello students, we are going to start a new chapter on theories of elastic failure today. In previous lecture we have already talked about the principal stress and principal strain, and we know that a component can be subjected to, let's say, biaxial state of stress or biaxial state of stress along with the shear stress, and we also calculated the value of the principal stresses, which are three mutually perpendicular planes, and we also calculated the value of maximum shear stress and using the Morse circles, and all these exercises we have done so far. Now we know when we do the tensile test, in that test the component is stretched uh, up to its elastic limit, okay, and beyond the elastic limit, if the component is stretched, then there is always a permanent deformation set into the material. So a component is considered to be failed if it has crossed its elastic limit stress value, that is measured in the simple tension test. And such kind of test or the results of such kind of test shall be applicable to all those cases when the component is simply subjected to only tensile stresses only, and that too in a one single direction. Now what happens is that in actual real life condition of the engineering components, we often tend to get the conditions which are not so simple as given in the simple tensile test. So the component may be subjected to, let's say, the stresses in two directions, and they may be of same nature, of differing nature, and it may also be subjected to the shear stresses along with the tensile stresses or compressive stresses that we see in the case of we were drawing the relation for the principal stress and principal strain. We have seen all these cases. So therefore the criteria of failure that a component has reached to its elastic stress values will not be applicable for these complex cases. So I can sum it up like this, that in case of materials subjected to simple state of stress, let's say tensile or compressive failure, is said to occur when the stress in the material reaches the elastic limit stress. And this elastic limit stress for each material is determined individually by experiment. So you can have ductile material or brittle material, you can have cast iron, mild steel, you can put up the specimen for any of these particular material in your tensile testing machine, and you can find out what is the value of elastic limit stress for these individual materials. Now these results are not applicable for material which are subjected to complex stress, which I just described you. So in this case, either experiments are to be performed for each set of such complex stresses which are acting, and this is impractical. We cannot have all such variety of cases, and we can't perform the test in all such conditions, okay, so that is impractical. The other approach is to evolve empirical formulas to satisfy the results in case of materials subjected to complex stress. So this is the second approach that we are talking about. Here we try to evolve the formulas which can satisfy the results in which we have the complex stresses. Non-availability of any one theory to all such state of stresses and all materials has resulted in propagation of different theories relating to complex stress to the elastic limit in simple tension or compression. Okay, so what basically we are trying to say is that we try to bring out those empirical relation, and we try to find certain values of those through those formulas, and we try to relate it with the elastic stress values which were calculated in simple tension test or compression test, and we say, okay, this value has reached to this value, and in the complex stress, then we say that the component has failed. So there are various theories which have been evolved over the period of time, and all these empirical relations are available with us, but there is not one single theory which is applicable to all sort of material, that means ductile and brittle material, and there is no one single theory which is applicable to all state of stresses as well. So that means one theory is not there will be multiple theories. That's why we call it as theories of elastic failure, and we are going to discuss them in detail now. So despite considerable experimental data on various stress system and also on different materials, no definitive and deciding evidence has favored any one particular theory of failure. So we will use these theories of failure judiciously depending upon the case to case, whether with what kind of loading we have on the component and what kind of material that we are considering for the analysis. In case of brittle material, just for example, in case of the brittle material, the maximum principal stress theory fits well. So it is very common theory which is used, and we call it as maximum principal stress theory. In a moment we are going to also read about that, what is that maximum principal stress theory. But just for the sake of information, I would like to tell you that the maximum principal stress theory works quite well for the brittle material. But in case of ductile material, the maximum shear stress theory or strain energy theory should be used. Okay, so if you have material like mild steel or similar aluminum, then the maximum shear stress theory works quite better there instead of maximum principal stress theory, and or maybe strain energy theory. Now, depending upon the type of loading, I would say that the shear strain energy theory is preferred if the mean principal stress is compressive in nature. So I can conclude that since the complex stress system can be simplified into three principal stresses, the problem reduces to link these principal stresses to the stresses at elastic limit in case of simple stress. Okay, so in all these complex state of stress, whether we have a biaxial state of stress or triaxial state of stress, or the shear stress is also acting on the component, we can always calculate the principal stresses by the formulas that we have discussed in our previous lectures, and or you may be using the Mohr circle, and we can find the value of these principal stresses for all these complex state of stress, and we can relate these principal stresses with the elastic limit calculated in the case of simple stress, and all these theories are doing this in one or the other way. Now let's consider these theories one by one. Before we start this discussion, to freshen up the memory, we have talked about the principal stresses. These are the planes, these are the stresses which exist on the planes, on which the shear stresses are 0, and these are existing on three mutually perpendicular planes, and their values are generally given by sigma 1, sigma 2, sigma 3, and you can have a situation when sigma 1 is greater than sigma 2 is greater than sigma 3, and so on and on. One of these or maybe two of these may be 0 in some cases also, so it may also be possible, and these values may be positive or negative depending upon the conditions. So let's assume, let's give the symbol that sigma et is the elastic limit stress in tension. So this is the value in the simple tensile test that you measured through the stress strain diagram. Okay, this is my elastic limit. You must have remembered that beyond your proportional limit, the elastic limit is there. Okay, so the elastic limit point after which there is a permanent set in the component. So that particular point till the time where it follows back the original curve in the stress strain diagram and reaches again back to the origin without having any permanent deformation in the system is termed as your elastic limit stress. So that limit maximum value of load stresses that the component can be subjected in elastic zone is called elastic limit stress. So sigma et is sigma elastic limit stress in tension, and sigma ec is your elastic limit stress in compression. So first theory amongst them is the maximum principal stress theory. This is the simplest and one of the oldest known theory. It is also termed as Rankine's theory. Okay, so this is also another name of this theory, Rankine's theory. Very commonly it is used as maximum principal stress theory. Now the statement of this theory is that it states that material fails when the maximum principal stress tensile reaches the elastic limit stress for the material in tension. So if your sigma 1, sigma 2, sigma 3 you have calculated, and the sigma 1 is the maximum amongst them, all the three values calculated, so it says that the material will fail when the maximum of these principal stresses tensile, that is sigma 1, reaches the elastic stress limit, that is sigma et, for the material in tension. Or if you have compressive loading, then obviously the sigma 1, sigma 2, sigma 3 may be in negative values, or maybe one of these may be in the negative values. So in that case the minimum principal stress compressive reaches the elastic limit stress for the material in compression, simple compression test. So that is it. So this is the statement of our principal stress theory. So basically we are comparing the value of the principal stress with the elastic limit stress in tension or compression. So this is just the reminder that the formula for the principal stress was sigma 1 oblique 2 or 2 is given by sigma x plus sigma y by 2 plus minus under root sigma x minus sigma y by 2 whole square plus tau x y square, where sigma x was the stresses that is applied along the x-axis, sigma y is the normal stresses applied along the y-axis, tau xy was the shear stress. These sigma x, sigma y can be tensile or compressive, or they can have they both may be tensile or they both may be compressive as well. So by this formula one we can calculate the value of sigma 1, which is coming with the positive sign here, and sigma 2 which is coming with the negative sign here in this formula. So after calculating the principal stresses, we say that according to this theory, the material fails when this principal stress value is equal to the elastic limit stress for tension or compression. So if you are using a positive sign, then it should be equal to sigma t. So if the calculated value of this sigma 1 becomes equal to sigma et, the component is going to get failed. Okay, so if it is equal to or greater than sigma et, the component will fail. Or if you are taking the minus sign, then the value should be equal to or greater than sigma ec, the component may fail. You must have remembered the discussion we had on the factor of safety in our initial classes. In our first lectures, we discussed about the factor of safety. So if you know the factor of safety of the problem, then the sigma et value may be reduced by permissible value of stresses by obtaining it by sigma dividing it by factor of safety n. So if you know if you are given in the numerical that the n is the factor of safety, the always factor of safety is greater than 1. So if you are given that okay, factor of safety is 2, factor of safety is 3 or 1.5, you simply divide the value of elastic limit stress with that particular value of factor of safety, and then you compare it with the principal stress value. So that is the one way to calculate it. So this theory, as I told you, works quite well for the brittle material. So this theory, though it works quite well for the brittle material, but it has a contradiction that it doesn't work for the ductile material. The simple reason is that the failure of the ductile material in simple tension is not caused by tension itself, tensile stresses. It is caused because of the shear stresses by sliding at 45 degree with the axis of the specimen. If you look at the specimen of a simple tensile test, I have also told you when we discussed about that tensile test in our initial lectures that the failure of the component will be always in this shape. Okay, so it is like a cup and cone shape. This is a cup and this is a cone shape. So you are applying the load perpendicular to these cross section area. Failure is occurring like a cup and cone shape, so that is occurring at 45 degree to the axis. So why is it happening? Because at 45 degree the shear stresses are maximum that we have calculated in case of when we discuss the principal stress chapter. You can go and look at that derivation again. So we said that okay, when we apply the one single axis stresses, the plane at 45 degree contains the maximum shear stress. So we see here in the simple tensile test for a ductile material, the failure occurs in a cup and cone shape, and that indicates that the failure is occurring at 45 degree to the axis, and they are occurring because of the maximum shear stress, not because of the tensile stresses. So therefore this is in contradiction to what we have talked about here, that the failures are occurring because of the tensile stresses, the sigma et. So that's why this theory doesn't work for the ductile material. So we don't apply this theory for the ductile material. We use it only and only for the case of brittle material. So please do remember that the principal stress theory should be utilized for the case of brittle material. Now let's talk about the next theory, that is maximum principal strain theory. Okay, this is also called as Saint-Venant's theory. So the statement of this theory goes like the failure of the material occurs when the maximum principal strain at a point in it reaches the strain at the elastic limit in simple tension, or when the minimum principal strain at a point in it reaches the strain of elastic point in simple compression. So if I put it in simple word, this definition, this is saying that instead of comparing the stresses from the simple tensile test, you better compare the strain values which are occurring in the system. So you calculate the value of principal strain. In our principal stress and strain chapter, we have talked about how to calculate the principal strain also. We also talked about the more circle for the strains also. So we know that how to calculate the principal stress for a complex state of stress. So that exercise we have already done in our previous class. So this particular theory is saying that if you calculate the principal strain for the complex system and you compare it with the elastic limit strain of the simple tensile test, then if it exceeds that values in the complex system, the component will fail. So that is what it is saying. So in case you have sigma 1 greater than sigma 2 greater than sigma 3, as we discussed here, and the value of strain, the formula for the strain will be sigma 1 by E minus mu times of sigma E by mu times by E into sigma 1 plus sigma 2 plus sigma 3. So that is the value of principal strain in one direction. So this principal strain in the direction 1 should be greater, if it becomes greater than sigma Et by E. Sigma Et by E, sigma Et is the tensile stress at the elastic limit, okay, and E is the modulus of elasticity. So if you divide the stress by the modulus of elasticity, you will get the strain values for a unique new axial state of stress. So if the value of this calculated value of strain, the principal strain, is greater than or equal to sigma Et by E, your component is going to get fail. Okay, this is what this is saying. And if you have compressive strains, so that means if you calculate the strain in the third direction, sigma 3 by E minus mu times mu by E into sigma 2 plus sigma 3 should be less than or equal to sigma EC by E for the component to remain safe. And if the component is failed, that is happening because if it becomes greater than or equal to sigma EC by E, so the component will fail because of this condition. So you see here, instead of comparing the stress values, we have compared the strain values. Now where does this theory fits? So the results of this particular theory provide a very good match in case of biaxial tension of the brittle material. So if you have like a brittle material, let's say cast iron, and you have the, let's say, some biaxial state of stress, there is a stress in the x direction and y direction, normal stresses that you have applied. So this theory works quite well for such kind of a situation. Okay, but the results do not match in case of ductile material biaxial tensile stress and brittle material under hydrostatic pressure. So if you have a case in which a brittle material ball, let's say a ball is submerged into water, so the pressure is being applied from all three sides, so that is called a case of hydrostatic pressure. Okay, so in such cases, even for the brittle material, this theory is not going to work well. Why is it so? Please try to find the answer for that. So the results do not match in case of ductile material for biaxial tensile stress, and they also do not match well for the brittle material under hydrostatic pressure, but this theory works quite well for biaxial tension of the brittle material. Now next theory that we will talk about is maximum shear stress theory. Okay, this theory, which is also known as Coulomb gas theory, is also very popular theory, and this theory is very widely applied for the case of ductile material. The statement of this theory goes like that: a material fails when the maximum shear stress in it reaches the maximum shear stress at the elastic limit in simple tension. Okay, so what is it saying? That maximum shear stress in the complex state of stress that you have calculated, tau max, reaches the maximum shear stress at the elastic limit in simple tension test. So that means in simple tension test at 45 degree there will be a plane where the shear stress shall be maximum. So you are going to calculate the value of the maximum shear stress for a at the point of elastic limit in the case of simple tension test by knowing how much is the stress for normal stresses. So you can always calculate half of it, that will be the your maximum shear stress in the case of simple tensile test. So sigma Et by 2 will be the value of maximum shear stress in case of simple tension, and if this value of the maximum shear stress that you have calculated becomes greater than or equal to sigma Et by 2, then the component will fail. Okay, you must have remembered the Mohr cycle, and we talked about that. If you calculate the maximum shear stress, how are you going to do that? Can you remember that? Okay, please go again and have a look how we are going to calculate the tau max in the case of complex state of stress. That means biaxial state of stress, including the shear stress is also present in that. So since the maximum shear stress in simple tension is equal to half the tensile stress, So the maximum shear stress, the formula for the maximum shear stress in the case of a complex state of stress is in terms of principal stress is given by sigma 1 minus sigma 2 by 2, right? It is under root of sigma x plus sigma y by 2 whole square plus tau xy square, right? So you can also obtain it by simply making the difference of the two principal stresses and dividing it by 2. So that also is equal to your tau max. Now if it becomes equal to or greater than sigma et by 2, which is the shear stress values at the tensile test, then the component will fail. You can simply simplify it by this 2 and 2 will get cancelled out. So it will say that the difference of the principal stresses should be less than or equal to sigma et for the component to remain safe. And if the difference of the principal stresses is greater than or equal to sigma et, your component is failing. Okay. So this theory gives fairly close results for the ductile material. It is very good for the ductile material. In fact, it is the most commonly used theory for the ductile material. Like as I told you that the principal stress theory is the most commonly used theory for in general for the brittle material. So maximum shear stress theory is the one theory which is most commonly used for the ductile material, and it is a simple and most commonly used, as I told you. The brittle material, it doesn't work good, so it doesn't provide very good result, because we know that in case of brittle material the failure occur because of the normal stresses, not because of the shear stresses. So if you take the cast iron specimen and if you apply the tensile load on the cast iron specimen, you stretch it in a simple tensile test, it will fail exactly at the 90 degree to the load application axis, right? Why? Because this is the axis where the normal stresses are the maximum. Okay, it will not give you the cup and cone shape. It will always fail at the 90 degree, right? So the brittle material, this theory is not going to work because it is talking about the maximum shear stress, and the brittle material fails primarily due to the normal stresses, not because of the shear stresses. In contrast, the ductile material fails because of the shear stresses. So therefore this theory works quite well for the shear stresses. Now under hydrostatic pressure, maximum shear stress is 0. So you see, when you have the hydrostatic stress, the sigma 1 becomes equal to sigma 2. So this will become 0. So that's why it is not going to work there. So under hydrostatic pressure, maximum shear stress is 0, and according to this theory no material should fail, which is incorrect. So in case of, we know that if you apply a very large amount of hydrostatic pressure, the component is going to get failed. So that's why this theory, as it is mathematically going to predict that the component will not fail, is not true, and this theory cannot be applied in such cases. Now there are some other theory left, but we'll continue our